Hi folks, welcome to this pre-work video in which we're getting ready to introduce the idea of a double integral in class. So a lot of the ideas that I'm going to show here in this video are just meant to be an overview, and we'll be developing them a little bit more carefully in class in our regular class. But I wanted to go ahead and expose you to these ideas now. So the second half of Calculus 1, the goal was to develop what we called the Riemann integral. The Riemann integral was built to determine what we called the net area between a curve, and curves in R2 look like just f of x, if we think of them as well-defined functions, and the x-axis. Okay, so that was the tool that we developed during the second half of Calc 1, the Riemann integral, and the purpose of the Riemann integral was to to compute the net area. So now we're going to develop the double Riemann integral, and in fact later on in this chapter we'll develop the triple Riemann integral. But the purpose of the double Riemann integral is to determine not the net area but the net volume between a surface f of xy, that's how we denote a general surface in R3, and the xy plane. Okay. So let's quickly work with this vocabulary, where if the function was greater than or equal to 0 in Calc 1, then we computed the definite integral, this Riemann integral. We were finding the area, not just the net area beneath the curve. And so that fits with our traditional sense of what we mean by area when we compute the definite integral of a function that is always greater than or equal to 0. So likewise, the same thing holds in Calc 3, that when we deal with a surface whose z values are always greater than or equal to 0, then when we compute this double integral here, and by the way, this is how we denote a double integral. It's simply the double integral bar, and then in this case, if it's over the region R, we write that region below there. Okay. And this will give not just the net volume, but the total volume. Again, if the function is always outputting positive z values, we compute the total volume. So you can think of the double Riemann integral then as a tool for computing total volume between a curve and between a surface, and the xy plane. Okay. So we're going to develop all these ideas much more carefully, but I just want to look at this picture, this visualization of what's going on here. So this was our strategy on the left-hand side here. This was our strategy in Calc 1, where we're trying to compute, in this case, the net area between this curve f of x and the x-axis. And so we have our two limits of integration, x equals a, x equals b. And so we're trying to compute this area right here. And our strategy was to compute a Riemann sum and then look at the limit as the number of rectangles in that sum went to infinity, or put another way, more precisely, as the widths of these rectangles, which is represented by delta x, as those widths go to 0, then this Riemann sum becomes a better and a better approximation for the area beneath the curve, and if that limit exists, then we call it the Riemann integral. So again, what did we do? Well, we chopped up the region that we were dealing with, in this case the region between x equals a and x equals b, into these subregions, and from each subregion we took a point from inside of that and evaluated that in the function. So that gave us a little, and here's the key part right here. When we plug each of those points from each rectangle into the function, that gives us a height. We multiply by that common width, and that gives us an approximation of the net area between this curve and the x-axis. So in Calc 3, we're going to start off by developing an approximation method and then look at that limit. And our strategy here will be to take, if we want to approximate the volume of this curve here I'm thinking of this as total volume or net volume, it doesn't matter. But if we want to compute the volume beneath this surface here and the xy plane, then what we're going to do is we're going to take a bunch of little rectangular regions. So maybe here is just, we've got this grid of all these different rectangular regions, and here is maybe one of them. So this is maybe the ith, or we'll use the book's notation, the kth rectangle. And what are we going to do? We're going to take some ordered pair from in there, x, xk star, yk star, and this is in the xy plane. We're going to plug this into the function, and that's going to give us a height that we're going to think of as the height of a column. Okay, so rather than using rectangles to approximate the area underneath the curve, we're going to add up the volumes of a bunch of columns in the living in 3 space to approximate the volume underneath the curve. So again, our approximation will be that the volume is approximately the sum of each of these f xk star yk star, then multiplied by whatever this area is here. And I'm going to call this area here, the area, each one of these is going to be delta A. That stands for the area of that particular rectangle. So if we add up all of these for each of our k rectangles, for k equals, should we start this at 1 to n, this gives us an approximation. That is, we're going to add up. Notice that this is a height, and this is a volume. And so what's their? This is a height and an area. And so what is their product? Their product is a volume here. So we're adding up the volumes of each one of these little columns that you see depicted here, and that's going to give us an approximation for the volume underneath the curve. So let's just finish this out here. What I just said was essentially this. In class, we'll be more careful with this, but for right now, we use just as we use these rectangles in here, so in Calc 1 we use rectangles, all of a common base width delta x, to approximate the net area between the curve and the x-axis. We're going to use columns with base area, we'll denote that by delta A, to approximate the net volume between the surface and the xy plane. So I'll see you in the next video as we actually start looking at putting this into practice.